Okay, so hello and welcome back. So in the previous videos we talked about a point. Basically we talked about suppose that we had this line segment, for example AB, and then we had some point, for example over here C, which was basically dividing the line segment AB in the ratio, for example in the ratio m to n, or we had this was and basically the line that the point C is dividing the line segment AB internally in this ratio. Now there was some other case where we had this, for example this line segment AB, and there we had some other point C which was dividing this line segment externally in some ratio, for example in some ratio m to n, for example m to n basically. And we talked about these, and we got a couple of formulas for these different situations. So now what we want to do, we want to basically extend this idea. We want to extend this idea to three-dimensional geometry. These were just about basically two-dimensional geometry. All of these points had basically coordinates x comma y, for example x1 comma y1, x2 comma y2, and so on and so on and so forth. Now we want to know what happens if you have basically if you are in three-dimensional space. Let's say that this is your x-axis, this is your y-axis, and this is your z-axis, and you have, for example, 2 points over here, A and B. And for example, if basically there is some point dividing this line segment in some ratio, for example call it point C, then what are the coordinates of this point C over here? That's what we want to find out now, and basically derive some formula, derive the coordinates of the point C in terms of the coordinates of these 2 points, and basically the two ratios, or the ratio basically. So what we want to do in this, basically that's all that we want to do in this video. Now the situation that we have is basically we have a three-dimensional coordinate system, and which looks something like this. This is your x-axis, this is your y-axis, and this is your z-axis. And we have 2 points over here, P and Q. You have a point over here, let's call it P, for example. We have another point over here, let's call it Q. And there is a line segment connecting these 2 points. So let these 2 points be, let the 2 points be basically P with coordinates x1, y1, z1, and Q with coordinates x2, y2, and z2. And also let the point R with coordinates x, y, z divide PQ in the given ratio m to n internally, of course, internally. So all of what we are doing over here is about internal division of a line segment in 3D space. But of course we can extend that to external division of a line segment in 3D space as well. That would not be a problem. So suppose that, for example, the point R, for example, is somewhere over here. Now what you need to do, you need to draw from these 3 points. You can basically produce some perpendicular lines to the XY plane down here, the horizontal plane. So I create a perpendicular over here, some perpendicular, for example, over here, and then if I connect these 2 points together because they are in the XY plane, and then I create a perpendicular from this point as well, and call these points, for example, LN and M. LN and M. So then you can draw the PL and QM and RN perpendicular to the XY plane, and of course you know that these lines are all parallel because they are all perpendicular to the same plane. So then you can say that PL is parallel to RN is parallel to the QM, and the feet of these perpendiculars are of course on the XY plane, meaning that the feet, of course you know that the feet of these perpendiculars are on the XY plane. Now the points L, N and M, so the points L, N and M will lie on a line which is the intersection of the plane containing these 3 lines, of the plane containing these 3 lines, PL basically RN and QM with the XY plane. So they basically, these 3 points over here, they lie on a line which is the intersection of 2 planes. So always the intersection of 2 planes is a line, and basically now these 3 points, they lie on a line which is the intersection of this plane that contains these 3 lines and the XY plane. Okay, so far we have no problem. Now through this point R, you can draw a line perpendicular to the parallel to the line LM. Okay, so through the point R, draw a line ST parallel to the line LM. So if I were to do this, I would, of course I would have to basically change this a little bit, because otherwise this line seems to be already perpendicular. So I'm going to basically move this a little bit down here. I'm going to basically do it like this. For example, something like this. This point would be P, this point would be Q, and this point would be R, basically. And then suppose that the construction is something like this, and then you can basically, through the point R, if I were to draw a line which was perpendicular to the line LM, I would draw a line like this, something like this. Now suppose that this line is perpendicular to LM. Okay. So what happens is that you will get a line over here. If I extend PL, basically this point, for example, S would be the intersection of this line and the line PL, and this point of intersection over here, I can call it, for example, T. And this line goes through R, is perpendicular to the LM. And so you can see that now basically you have a parallelogram over here, SLMT, and basically these two are also parallelograms, meaning that SLNR and RNMT are also parallelograms. And that's basically, and we did this on purpose because we actually wanted to get a parallelogram, since we do need it in order to derive a couple of things in this construction. So basically you understand that these two, basically it is obvious that SLNR and RNMT are parallelograms. And we have already talked about similar triangles. So these triangles that you see over here, PRS and QRT, also triangle PRS is similar to triangle PRS QRT. And one thing that you need to remember about similar triangles, I haven't found the right place to talk about similar triangles in detail, has not come up yet. It's basically, it's a pretty long story. It would take up at least 4 to 5 videos, even more than that, to go through, meaning at least 4 or 5 hours to go through similar triangles. And as I mentioned before, there is similar triangles. And there is also congruent triangles. These are basically two different things, two different concepts, both related to triangles. But one thing that, if I were to add something to what I've already said about similar triangles, is that basically when you have two triangles, like for example, let's say that this triangle is similar to this triangle. Let's suppose that these triangles are similar. For example, this angle is equal to this angle is equal to this angle, and this angle is equal to this angle. And let's say that this triangle is ABC and this triangle is DEF. So now if I want to write that these two triangles are similar, I can write triangle ABC is similar to triangle DEF. but there is a correspondence between the angles of this triangle and between the sides of this triangle, meaning that basically this side of the triangle corresponds to this side of this triangle. This side corresponds to this side, and this side corresponds to this side. And you cannot say that, for example, this side corresponds to this side of the triangle, because then everything will just simply fall apart. So what you want to do is that you cannot, for example, based on all the correspondence there is between the sides and the angles of these two triangles, you have to put the vertices in the right order, meaning that you cannot write, for example, the triangle ABC. You cannot write the triangle ABC, for example, is congruent to the triangle, for example, FED, for example. That would be wrong, because then that would mean that the vertex F, for example, in this triangle corresponds to vertex A in this triangle, which is not true. So you cannot write this. You have to write it in the right order. So that's basically one thing. So as you can see, I have basically taken care of that already over here, meaning that when I want to write that these two triangles are similar, I have written basically the triangle PRS is similar to the triangle, to this triangle QRT, meaning that what that means is that, for example, this side length, for example, PR corresponds to this side length QR over here. So when I start with this vertex over here P, then I have to start with this vertex Q up here, and not this vertex over here or this vertex over here. And you see that since, for example, these two vertices correspond together, R comes to R, P comes to Q, for example, and S comes to S, basically corresponds to T. So you need to take care of that notation over here. Otherwise, it would simply be wrong, and then somebody else could, based on what you've written, somebody could write something wrong about these two triangles, assuming that you knew what you were doing, and then the whole thing basically would be wrong. So you don't want to do that. So then these two triangles are similar, right? So then based on the similarity of these two triangles, we showed that, I think it was in the previous videos, that basically the side ratios remain constant, meaning that, for example, if two triangles are similar over here, suppose that you have these two triangles are similar, then ABC, DEF, for example, you can say that triangle ABC is similar to the triangle DEF, and then based on that you can say that AB to DE is equal to, for example, AC to DF. AC to DF is equal to, for example, BC to EF. So these ratios always remain the same. But of course, again, over here you need to be careful, meaning that if you write the side of this triangle in the numerator here, again here you have to write another side of the same triangle in the numerator. Otherwise, of course, the ratio would not be right. Okay. So that's basically that. So then based on that, what I can write is basically M to N, which is and M is basically the ratio that we have here. We said that the point R basically divides the line segment PQ in the given ratio M to N. That means that we have taken this length as M and this length as N. Let me do it in this basically manner so that you can see it. So this is M, and this over here is N. Okay. So then what that means is that you can write, based on the similarity of these two triangles, you can write m to n is equal to basically is equal to PR to QR, so these are basically the same sides, PR to QR, which is equal to SP to QT, so these are another two sides of these two triangles, is equal to SP to QT, and of course SP over here you can write it as SL minus PL, and QT you can write it as QM minus TM, and then this ratio over here, or this fraction over here, you can write it as, well, SL you can write it as NR, because all of these lengths are the same. SL, you know that SL is equal to NR is equal to TM, of course, is equal to TM. So what that means is that instead of SL I can write NR minus PL, and over here I can write QM minus TM. Again, I can write it as NR, and well, this is equal to, now NR is equal to the coordinates of this point over here. The coordinates of the point R are basically, well, it's already written over here, XYZ. So NR is the Z coordinate of this point, which is equal to Z, and PL is basically the Z coordinate of the point P, which is basically over here. Let me write it down over here. So the point P, basically we said up here that basically point P was X1, Y1 and Z1, and the point Q is already over here. So then basically what we have is basically PL is the Z coordinate of the point P, which is Z1, so minus Z1, and QM is basically the Z coordinate of the point Q, which is Z2 minus NR, which is equal to Z. So what that means is that basically Z2, what that means is that M to N, the ratio, is equal to Z minus Z1 over Z2 minus Z. And if you want to find and now Z over here is basically the Z coordinate of the point that we were looking for. Basically we started this whole thing in order to find the X, Y and Z coordinates of this point R. So that means that the Z is already over here in terms of Z1, Z2 and M and N. So then I can write basically M times Z2 minus Z is equal to N times Z minus Z1, and so M times Z2 is equal to M times Z2 minus M times Z is equal to N times Z minus N times Z1, and over here, if I write negative mz minus nz is equal to negative nz1 plus minus m times z2. So I keep this over here and move this to the other side of the equation. It becomes negative nz, negative nz1 minus mz2. So if I multiply the whole equation by negative 1, I'll get mz plus nz is equal to n times z1 plus m times z2. And then if I take a z out here, I'll get m plus n is equal to n times z1 plus m times z2. And so z is equal to then n times z1 plus m times z2 over m plus n. Or basically to help yourself remember this better, you can write this as z is equal to m times z2 plus n times z1. And there is a reason why I'm saying this. It's because of it will fit together with other places that you use this formula, so it's better to learn it this way, meaning that z is equal to m times z2 plus n times z1 over m plus n. So that is the z coordinate of the point that you were looking for. Now similarly you can do the same thing, meaning that you can, using the same process right now, in order to find the z coordinate of this point, we had to drop 3 perpendiculars to the xy plane. Next you have the xz plane, and you also have the yz plane. So if from this point you drop some perpendiculars to the yz plane, you will find the x coordinate of the point. If on the other hand you drop 3 perpendiculars to the xz plane, you will find the y coordinate of that point. And so in the same manner, you will have the x coordinate and the y coordinate of the point as well. And so what you would get is that the y coordinate of the point would be m times y2. So over here you have m times y2. So here you have z, z2, z1, m times y2 plus n times y1 over m plus n. Okay, so that's one thing. And then if you drop some perpendiculars to the yz plane, you will get the x coordinate of the point, which would be x is equal to basically m times x2 plus n times x1 over m plus n over m plus n. And that is basically the x, y, and z coordinates of the point are basically, so basically you can say hence the coordinates of the point are the coordinates of the point R, which divides the line segment joining 2 points P and Q. So P was basically x1, y1, z1, and Q x2, y2, z2. internally in the ratio m to n are given by basically your x is mx2 plus nx1 over m plus n, and then the y coordinate would be my2 plus ny1 over m plus n, and then you have mz2 plus nz1 over m plus n, and that is the coordinates of that point. That is the coordinates of that point. Now there are also a few cases here that we need to talk about. Okay, so now there is a couple of special cases about this basically, about the coordinates of this point, the coordinates of the point that we talked about. And what that is that basically in the previous case, in the two-dimensional version of the same formulas and basically coordinates of this point, we saw that basically if you had some line like this, for example, some line segment like this AB, and if, for example, C was some point over here, if this distance over here was, for example, M, and if this distance over here was, for example, some distance like this, for example, N, and in this situation we said that basically the point C we said that the point C basically divides the line segment AB in the externally in the ratio m to n. And the formula that we got for this was basically C was basically m times x2 minus n times x1 over m minus n, and the y coordinate was m times y2 minus n times y1 over m minus n. And if you pay attention to this formula, you can see that your ends have become basically negative ends, meaning that all ends have become negative ends compared to the internal division of a line segment, meaning that we said that if basically point C, if point C divides the line segment AB, for example, internally, internally in the ratio m to n, then the coordinates of C would be, which is basically some situation like this. For example, A, B, and for example C over here, and this would be basically M, and this distance over here would be N. So this is internal division, and these are basically the ratios. So then the coordinates of the point C would be m times x2 plus n times x1 over m plus n over m times y2 plus n times y1 over m plus n. So now in this formula, if I take all of the, if I substitute n with negative n, what I will get is C is equal to basically m times x2 minus n times x1, m minus n, and over here I'll get m times y2 minus n times y1 over m minus n, and that's basically exactly what you have over here. So what that means is that the external division, the internal division of a line with a point, if you take the formula and substitute every n with negative n, you will get the formula for the external division of a line, the external division of a line segment with a point, basically. Now the same thing happens over here in the case of the 3D, in the case of the coordinates of the point in the three-dimensional system. In the three-dimensional system, we said that if we had basically P, for example, x1, y1, z1, and if we had Q as x2, y2, z2, and if you have some point, for example, R with coordinates x, y, z, dividing the line segment joining these 2 points P and Q, meaning that you have, for example, some P and Q over here, and R is basically over here, and this over here is M, for example, and this over here is N. So if the division is internal, then the coordinates of the point R are given by basically m times x2 plus n times x1 over m plus n, and the y coordinate is given by m times y2 plus n times y1 over m plus n, and the z is basically m times z2 plus n times z1 over m plus n. Now again, this is the internal division of this line segment with a point R, basically, in the ratio m to n. Now the external division of PQ, of basically the line segment PQ with the point R would therefore be, you take this equation, this coordinate, and substitute every n with negative n, meaning that then your R would be the coordinates of R would be basically m times x2 minus n times x1, m minus n, and m times y2 minus n times y1 over m minus n, and m times z2 minus n times z1 over m minus n. And that is basically that. Now there is, and of course you could of course derive this formula. I think we did derive this formula in the two-dimensional plane. You can derive this in the three-dimensional plane as well, and you will get this. You will get these exact coordinates. And now there is a couple of cases here that we need to talk about. Now, if basically the formula that we had was basically this thing over here. So let me erase these so that I don't have to write them again and again. So basically, if now the coordinates of a point, if r divides PQ internally in the ratio 1:1, that is if r is the midpoint of PQ, if r is the midpoint of PQ, then the coordinates of r would be basically your ratio would be 1:1, meaning that you would get r, the coordinates of r would be basically x1 plus x2 over 2, and y1 plus y2 over 2, and z1 plus z2 over 2. And these are basically the coordinates of the midpoint of the line segment PQ. So this is the midpoint. This is the midpoint. Now there is one more thing over here. There is another case over here. Then the coordinates of the point R, which divides PQ in the ratio k:1, are obtained by taking k as m to n. And so this is basically what we talked about in the previous video as well, about the two-dimensional plane and the section formula and so on and so forth. But if you take basically, let me go back over there, because I want to use this thing over here. So now, if you take now having this situation, then you can say that the coordinates of the point R, which divides PQ in the ratio k:1, are obtained by by taking k as m to n, by taking k as k is equal to m to n, which are given as so basically what you need to do here is that basically the ratio that we used over here was basically m to n. So if the ratio is m to n, then you can, of course, you can take the ratio, then you can take the ratio as the ratio becomes k to 1 if you take k as m divided by n. If k is equal to m divided by n, then k to 1 becomes m divided by n to 1, which is the same thing as m divided by n divided by 1, which is equal to m divided by n, which is the same thing as m to n. So the ratio remains the same over here. So in many situations, basically this can be helpful in solving problems, meaning that any ratio really, as and we talked about this in the previous video as well, any ratio can be expressed as, any ratio m to n can be expressed as either 1 to k or basically k to 1, meaning that one of the numbers you can take as 1. And so and by doing so, basically what happens is that now in this case, for example, if these two were unknowns and you were to find them, you would have two unknowns over here. But in this case, you would have only one unknown, and it would be easier to find one unknown rather than having two unknowns. And so basically what that means is that if you take, for example, in the same situation, if you take k as, for example, if you take k as n to m, for example, take k as 1 to m, then you can rewrite this as basically 1 to k. And what that means is that then it would be basically 1 to basically n to m, which would be the same thing as 1 over n to m, which is equal to m to n, which is basically the same ratio again over here. So depending on the situation, you can basically somehow play with your ratios to get the right ratio over here. And now to get a 4 based on this whole story, if your ratio, if you take your k as basically m to n, then your ratio becomes, so basically the ratio originally was m to n. Now if you take k as m to n, then you would have basically then you would have your ratio as k to 1. Now k to 1 would be, and then based on this you could rewrite this formula as basically r as basically so k times x2 plus x1 over 1 plus k, and k times y2 plus y1 over 1 plus k, and k times z2 plus z1 over 1 plus k. That would be the coordinates of the point. assuming that you take the ratio instead of m2n, if you take it as 1 to k to 1, and of course we will do some examples to understand this concept better, and this concept is actually very helpful in many different situations. So that is basically the whole story here. Now we have a couple of examples over here, and we will do these examples, and we are almost done with this chapter. But of course you never know, because there is always something along the way that you have to basically always go back and take a look at, so you don't know how long it's going to take to finish something properly, but we are on the way. Okay, so now as an example, let's say we want to find the coordinates of the point. Find the coordinates of the point which divides the line segment joining the points 1, negative 2, 3, and 3, 4, negative 5, these 2 points, in the ratio 2 to 3. In the ratio 2 to 3, either internally and externally. So in order to basically, in order to find the coordinates of this of that point. So now if basically, suppose that your line is basically, the line segment is something like this. So suppose that this is your z-axis, this is your y-axis, and this is your x-axis, and your x is 1, your x is 1, your y is negative 2. So let me, basically I have to redraw these parts as well. I have negative numbers as well, and okay, so I have, this is your y is negative 2, so basically negative 1 and negative 2 over here. So if I extend this line over here and draw a line parallel, so that would be the point, and then I have to go 3 units up, so 1, 2, and 3 units up, and that's my point. That is my point. So this point is going to be the point, if I call it A for example, and this is going to be A. This is in the 1, 2, 3, and in the 4th octant. Now suppose that you have another point B for example, 3, so 1, 2, and 3, 4, so 1, 2, 3, and 4. This point over here, and I have to go down 5 units. So 1, 2, 3, 4, and 5. One, 2, 3, 4, and 5. So this point over here is now point B, and it is down here in the 1, 2, 3, 4, in the 5th octant down here, right? So now if I connect these 2 points together this way, I will have a point that goes from up here down to the 5th octant. Now suppose that there's a point that divides this line segment internally in the ratio 2 to 3. meaning that if the ratio is 2 to 3, what that means is that basically if a line segment, suppose that I have a line segment over here and I take a point over here and I call this point A, for example, and basically what I want to show you is basically what is exactly the meaning of the ratio 2 to 3 in terms of distances. So how I can basically show this, basically this ratio, is that I can but suppose that for example I take some for example some compass and do one marking over here, open my compass to some diameter and do one arc over here, another arc over here, another arc over here, another arc over here, and another arc over here. So of course I don't change the diameter of the compass. So all of these distances are going to be exactly the same. So you have 1, 2, 3, 4, 5 exactly equal distances over here. Now this point over here, if I take this distance, so this distance and this distance and this distance over here, the ratio of these, suppose that I call this C, for example, and I call this point B, then AC to AB is equal to 2 to 3. AC to AB is equal to 2 to 3, and of course you need to pay attention to the fact that basically I opened my compass. Okay, so now here you need to also pay attention to the fact that I opened my compass to just some arbitrary distance or some arbitrary diameter and drew these arcs over here, meaning that each of these arcs that you see over here, for example, that would be, for example, one arc, the distance of basically created by one arc. This distance could be 2 centimeters, it could be 5 centimeters, it could be 10 centimeters, it could be 10 meters, it could be 100 meters, it could be 100 kilometers. It doesn't really matter what the distance of each arc is, as long as, of course, every distance is equal to the other one. Meaning that whether, for example, suppose that, for example, this distance is basically 2 centimeters. Then 2 times 2 centimeters over here, you would have 4 centimeters, and that would be 6 centimeters. Now, 4 divided by 6 is equal to 2/3 is the ratio. Suppose that, for example, each of these distances is 10 centimeters. So then this would be 10 times 2 is equal to 20 centimeters, and that would be 30 centimeters. Now 20 centimeters by 30 centimeters would be basically 2/3. The ratio is 2/3 without any units. It doesn't even have a unit, it's just a ratio. So that's the meaning of the ratio 2/3. So now coming back to the problem, what we have over here is the ratio 2/3 internally. Okay, so what I can do is that I can take the point A as point 1, I can take the point B as point 2, the ratio I can take as 2/3, and it is internal. So the formula for this in 3D space is the point, if I call it C for example, the coordinates of the point C would be basically m times x2 plus n times x1 over m plus n, and m times y2 plus n times y1 over m plus n, and m times z2 plus n times z1 over m plus n. So now x1, x2, basically this would be x1, x2, x1, y1, z1, and this would be x2, y2, z2, right? So that's basically what I mean when I say point 1 and point 2. So then the coordinates of the point C would be basically m times, and this is m to n. That means that your m is equal to 2, your n is equal to 3. So then I can write 2 times x2. So it's basically 0.2. This is 0.2. So that would be 3 plus n times 3 times x1, which is equal to positive 1, over m plus n, which is 2 plus 3 is equal to 5. Then the next point is m times 2 times x2, 2 times y2, so y2 is positive 4, plus n times, n is equal to 3 times y1, which is equal to negative 2, over m plus n, which is equal to 5. And then you have m times z2, so 2 times z2 is equal to negative 5, plus n times z1, so 3 times z1, which is positive 3, over m plus n, which is equal to 5. Now you can simplify this, of course. You can write it as basically 6 plus 3 over 5. 6 plus 3 over 5. Over here you can write 8 minus 6 over 5. And over here you can write negative 10 plus 9 over 5, which is equal to 9 over 5, 9/5, 2/5, and negative 1/5. So now in order to locate this point here, so the point would be 9/5 would be basically 1 and 4/5. So 1 and 4/5 along the x-axis would be some point over here, and then 2/5 is basically along the y-axis. So that would be 2/5 would be some point over here. Would be over here. And then you have to go down negative 1/5, which is, well, kind of the same point over here. So as you can see, the point is basically this point over here, and this distance is supposed to be, I mean, the ratio over here is supposed to be 2/3, meaning that the ratio of this, it doesn't mean that it doesn't mean that this distance is 2 times or 3 times this distance. The ratio of the two distances is 2/3, which of course makes sense based on this distance that I can see. And so, but well, the coordinates of the point are important. Is basically 9/5, 2/5, and -1/5. So over here I can write 9/5, 2/5, and -1/5. That is one thing. That is the first part over here. Now the second part, is you have basically a point that divides this line segment. You have a point that divides this line segment externally in the ratio 2 to 3. So basically we said that when the division is external, you use the same formula essentially, meaning that for example, if I call the point C, it's going to be the same formula, except that every n becomes negative n, meaning that m times x2 minus n times x1 over m minus n. Every n in that original formula becomes a negative n. Or the y coordinate becomes m times y2 minus n times n y1 over m minus n. Or you have basically m times z2 minus n times z1 over m minus n. So now what I'm going to do is that take this point A as x1, y1, z1, and take this point as x2, y2, z2. And the ratio is 2/3. So then the coordinates of the point C are going to be, okay, so then the coordinates of this point C would be, basically we said that m is equal to, we said that m to n is equal to 2 to 3. That means that your m is equal to 2 and your n is equal to 3. So m is equal to 2. So 2 times x2. Now x2 is basically this coordinate over here, minus n times x1. 3 times x1. Positive 1. Over m minus n, 2 minus 3. Your y coordinate would be m times y2. So that would be 2 times 4. That would be 2 times 4. 2 times 4 minus n times y1. 3 times -2. 3 times -2. So n times y1 would be 3 times -2. m minus n would be 2 minus 3. And the z coordinate of the point would be mz2, 2 times -5. 2 times -5 minus nz1. 3 times 3. 3 times 3 over 2 minus 3. Which is equal to basically 6 minus 3 over 2 minus 3. Over 2 minus 3, comma 8 times 8 minus -6 over 2 minus 3. And over here you have -10 minus 9 over 2 minus 3, which is equal to which is equal to basically 6 minus 3 is equal to 3 over negative 1. This is 8 plus 6 is equal to 14. 14 over negative 1 and negative 19 over negative 1, which is equal to basically negative 3, negative 14, and positive 19. Negative 3, negative 14, positive 19. Negative 3, negative 14, and positive 19. So this point would be negative 3 would be 1, 2, and 3 over here. And negative 3 would be, negative 14 would be here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. And that would be some point over here, some point over here. And then I have to go up 19 units. 19 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So now if I basically now this point is supposed to be right over here, but my units are not perfect. So now what this means, if I assume that this point is over here, what this means is that basically this ratio 2 to 3 external, what that means is that basically this is point B, this is point A. What that means is that basically if I call this point C, that means that BC to AB is equal to, BC to AB is equal to, of course, 3 to 2. BC to AB is equal to 3 to 2. BC to AB is equal to 3 to 2, meaning 1, 2, and 3. And let me see what the point negative 3, negative 14, and negative 19. But I was expecting to get the point on the other side of the line, meaning down here. But I did get it on this side of the line. On this side, on this side of A, basically. I was expecting to get the point on the other side. But what this means is that basically, as you can see, this length BC the ratio of BC to AC to AB is actually 3 by 2. It does make sense because 3 to 2. Meaning that it is 1.5. Which doesn't make much sense. Well, what we can do is that we can find the distance between this point over here. We can find the distance of this point from, for example, from it doesn't make any sense to me. basically what we said about these external ratios was that if we had a line segment, for example AB, and if there was a point C, for example, if C divides for example AB externally in the ratio 3:1, for example 3:1, what that means is that then you would I would imagine that you would get a point over here C, and then A to C, this distance over here, AC to BC, is going to be equal to 3:1. That's what this means basically. And let me actually show you some what we had over here. You see over here we want to find out the point lying on the extended line AB outside of the segment AB, such that AC to BC is equal to 3:1. So we will say that the point C externally divides AB in the ratio 3:1. That means that AC to BC is equal to 3:1, meaning that this distance AC is equal to 3 times the distance BC. That's basically what this means. Now, what this is supposed to mean here, if in this situation I've gotten this point, and of course the point seems to be right because it's based on the point that we have in the book. The point is also the same point. Now we have our point A over here, we have our point B over here. So what this means is that the distance B to C is supposed to be, if I somehow make some changes to this ratio, I can get it, basically I can rewrite this as BC to AB. BC to AB is equal to 3/2 to 1, meaning that basically BC, and if you basically do cross multiply here, you'll get 3/2 AB is equal to BC. That means that BC, the length of BC is 3/2 the length of AB. And 3/2 is the same thing as 1.5. So 1.5 would be, well, of course in this coordinate system also there is a problem that the distances are not that obvious. I mean, you cannot, you think that you can see them, but what this means is that basically BC is supposed to be 1.5 times AB, meaning that this distance AB is meaning that this distance BC is supposed to be 1.5 times this distance, which of course well, as I said, these distances over here, the distances might actually lie to you. So what we can do is that we can actually take these distances and basically plot them over here. So let me actually do this, because I don't want to. I want to when you solve a problem, you need to understand what the answer represents. Otherwise, it doesn't make any sense to solve something and not understand it. So if there is another point 3, comma 4, comma -5. So these are the 2 points that we had, point A and point B. Okay, so these are the 2 points, and these are my of course this is the x, this is the y direction, and this is, as you can see right now, I have the negative y direction here, so I have to move this way to get it to the standard basically orientation. And now this is the positive y direction, this is the negative y direction, this is the positive x direction, negative x direction, and this is z and negative z and the negative z's. So you can see that your point, basically, your points are down here below the xy plane, or one of them is below the xy plane, one of them is above the xy plane, and this one is up here in the 1, 2, 3, 4th octant. The other one is down here in the 5th octant. Now if I go over here and do a segment between these 2 points, and then move it, and you can see that GeoGebra shows you this part in basically broken lines, meaning that this is now going through this plane, for example. Now the point that we found in the first basically the first answer that we found was 9/5, comma 2/5, comma -1/5, and that was basically this point over here, point C. This was the line that this was the point that basically divided the line internally. The line that divided the point that divided the line externally was -3, comma -14, comma -3, comma -14, comma 19, which is not there. For whatever reason, the point is not there. -3, -14, and 19. Where's that point? It's not showing me the point. So we can go over here. And I think if we zoom out or in or something like that, we will see that point. That there is the point, but okay, so what that means is that now if I connect these points together, I can do a segment between this point and this point, and now the points are connected together. Now I can move this. Now as you can see, this is the positive. This is the positive y's. These are the negative y's. And these are the positive x's, negative x's. So again, now there is a problem with this coordinate system that it doesn't really show you where you are exactly, in which quadrant you are. Because if I had for example, if I had maybe I could do a plane over here. You might be able to actually get over that problem by writing the equation of, for example, some plane that is perpendicular to the y-axis and basically parallel to the z-axis, and then basically goes through the two axes, and then that would be basically your basically YZ plane, for example, and then that way probably you could see the points better. But we will do that later, because I don't really know how to write the equation of a plane. So, but now what we actually can do is that, so what we can do is that we can find the distance between the point B and, well, for now we can actually ignore point C. If I want to basically settings, and then you can basically name C, definition, caption, show object, don't show object. So then you can, this way you can hide it. And then you can go back here and find the distance between D and B and A and B. So that you can do with GeoGebra. Otherwise you would have to do a whole lot of calculation to calculate the distance between these 2 points. So you can go over here and basically do, what is that? You can, there's some tab over here which is about measurement. So here you can go to distance and select this point and this point. And then you can come back over here, text DB, name D plus name B plus whatever that is, distance DB. DB is equal to 30.59. And then you can come back over here and do the same thing for the other 2 points, meaning that you can go to measure and distance, length, and now select A and select B, and it gives you 10.2. And so now I have these 2 distances. I can go back over here and see what we can do with these distances. So we said that the ratio has to be 3 to 2. So if I take the ratio of basically DB to AB, that's equal to 30.59 to 10.2. And if I 30.59 divided by 10.2, that gives me 2.999. But it somehow doesn't make any sense still. Well, one more thing that I can do, I can come back over here and measure the distance between these 2 points. It's 20.4. It's 20.4. 20.4. Okay. So now if I divide it, for example, let's say 30.59, which is basically the whole distance, 30.59 divided by 20.4, 20.4, that gives me 1.499. That is the ratio. That is the ratio we were looking for, 1.5, 3 by 2. That means that basically the ratio that we were looking for is actually this ratio over here, 30.59 to 20.4. 30.59, which is basically the distance between point D and point B, to 20.4, which is the distance between A and D. Which makes sense, but it's actually the other way around, meaning that it's not based on the definition that we had over here. It's actually the exact opposite of this definition, and then we've gotten the point C on the other side of the line. So we will check this in other examples as well and see what we get over there. But it's basically in agreement with this in a way, and also in some way not in agreement. So that's basically, but this basically the point that we got was actually correct, and the distances are correct, but you need to be aware of the fact that where you will get your point and what those distances actually mean. Okay, so so that is basically that. Now there are a couple more things to do over here. There is 2 more examples to do, 3 more examples to do. And these examples are necessary to understand these concepts. So I'll end this video here. We will do the rest of the examples in the next video, and we will see where that takes us. I'll see you in the next video.